discussing in the last module about the quasi-static analysis, and we figured out that for the 0th order only electric field E0 exists and magnetic field will be equal to 0, but we soon found out that that analysis is not correct. So, for the first order what we have obtained is the magnetic field, and that magnetic field is dependent on the derivative of the voltage. So, as long as dV by dt is non-zero, then that magnetic field would exist. But we assumed until this point that the electric field is uniform vertically down and it is varying with time, but it is independent of this direction r, right. So, that is the point of a uniform field. So, you take this top plate and the bottom plate, the electric field lines will all be uniform. This is what we had assumed, but clearly such an assumption is not correct, and there we enter into the so called second order effects. In the second order, the magnetic field that we found from the first order will induce a certain magnetic flux density which will be changing with time, that will induce a certain EMF. Okay. So, let us see that we have considered one loop here, okay, of the length r1 and the height h, because we have considered from the top plate to the bottom plate, and we are trying to apply an EMF Faraday's law essentially to this loop, okay, in the direction which I have shown by the green arrows. The electric field at the center is vertically down and it is given by E of 0. This was the same E of 0 that we found from the 0th order. So, which was E0 of 0, and this was given by V of t by h, right. So, this is precisely the field that we had found earlier, but this electric field is no longer going to be the same. For argument's sake, let us assume that the field here is E of r1. I have dropped the time dependence here, but you also need to understand that there is time dependence, but time is varying very slowly. Okay. So, in other words, frequency is quite small. So, this E of 0 multiplied by h will be the contribution of this segment 1. Segments 2 and 4 do not contribute anything to the EMF, because here the electric field is vertical, whereas the lines or the field, the loop that we have considered is horizontal segments for 2 and 4. The contribution from 1 and 2 will be in the opposite direction, because one is an integral from top to bottom, the other one is an integral from bottom to top. Therefore, the EMF around loop will be given as E of 0 h minus E of r1 into h. What should this be equal to? This should be equal to the magnetic flux density d by dt of magnetic flux density, okay, which I am denoting as phi mag. Okay. So, this is the equation. We will come back to the implication of this equation once we realize the right hand side, once we know the right hand side. I know what is the magnetic flux density B, and I know what is the area of this particular loop, right. So, if I want to find out what is the magnetic flux density for the same loop that I have considered, I need to integrate this one along say h, say 0 to h in one direction. That variable, let us call this as z. This is a loop in which your r is changing and z is changing, therefore, the area itself would be along phi, which is precisely the direction of the magnetic flux density vector as well, right. So, put down the magnetic flux density mu 0 epsilon by 2 h and then dV by dt. Okay. Everything is a constant, so you can easily move everything out, but you have r here, okay, as part of the magnetic flux density itself. So, this is part of the magnetic flux density, but the loop itself, since you are considering r and z, the loop area would be r dr. Okay. So, this would be r dr, and the integration is from 0 to r1. So, r equal to 0 to r1 and integration along say dz. So, clearly integration along z will give one h, that h will cancel the h in the denominator. So, the magnetic flux density that you will get will be equal to mu 0 epsilon by 2, okay, dV by dt, and you will have an integral of r dr from 0 to r1, which would be r1 square by 2. So, you will have r1 square, and there is a 2 in the denominator already. So, this becomes r1 square by 4. So, this is the magnetic flux density, and the time rate of change of magnetic flux density is clearly d phi mag by dt is equal to mu 0 epsilon by 4 r1 square, which is now a constant, d square v by dt square, correct. this quantity must be equal, or the minus of this quantity, negative of this quantity must be equal to this E of 0 h minus E of r 1, which will allow me to write down E at r 1 minus E of 0 is equal to mu 0 epsilon by 4 h r 1 square d square v by dt square. In other words, E of r 1 is equal to mu 0 epsilon by 4 h r 1 square d square v by dt square plus E of 0. This equation is a big change from the electric field that we had assumed. What it means is that the electric field at the center, which is E of 0, is not the same as the electric field at any other distance r 1, correct. So, this electric field, so where this is r 1, the electric field is not the same at this point. So, these two are not equal, which means that the field lines are not uniform as you go along the capacitor plates. Okay. So, as you move from the center and you keep going along the capacitor plates, the electric field has become non-uniform. So, the E field is non-uniform. Okay. In fact, we really do not know what is E of r 1. We can actually obtain the relationship for E of r 1, because I know that this equation can be applied at the boundary condition, right. So, at the edge, and at the edge I know what is the EMF, right. So, go back to this first expression and then imagine yourself having a loop here. Okay. So, you imagine a loop at this case, and there is no contribution here on the horizontal edges from the top and the bottom, and here whatever the electric field that would be there would be the electric field at r equal to A times h must be equal to V of t. So, now I already know how to obtain E of r, okay, r 1. So, if I substitute r 1 is equal to A, then the total electric field must be equal to that V of t by h, correct. So, indeed the condition is that E at r 1 is equal to A must be equal to V of t by h, correct. So, this will enable us to basically find out what is the electric field. So, we will write down this as E at r 1 is equal to A, okay, which is basically V of t by h, that must be equal to E of 0. This will actually enable us to find E of 0. So, plus mu 0 epsilon by 4 h, and r 1 is equal to A becomes A square d square V by dt square. So, rearranging this equation, you get E of 0 as V of t by h minus mu 0 epsilon by 4 h A square d square V by dt square. You can substitute that into this expression to obtain electric field E at any distance r, along the capacitor, the direction that we have shown, is equal to V of t by h minus, and then I will have A square minus r square, okay, times d square V by dt square. This is the electric field at any distance r from the center of the capacitor plate. So, this is the center, and if you go along the direction r as I have shown here, this would be the electric field, and clearly this electric field is non-uniform. Okay. Now, the only thing that we would like to know here is what is the EMF around the loop, right. So, or what is the EMF that is induced from the center at axis rho equal to 0 to the outer edge of the capacitor. The EMF in fact is given by E of r into h. So, we can write this as EMF at any r, okay, that would be given by the electric field magnitude E of r into h will be equal to V of t minus mu 0 epsilon by 4 A square minus r square times d square V by dt square. So, as long as you have d square V by dt square changing with respect to time, then you will have an EMF which is different. Okay. What is the EMF at the center? At the center, EMF at r equal to 0 is given by V of t minus mu 0 epsilon by 4, and r equal to 0 will be just A square d square V by dt square. In fact, this is what we have obtained earlier. So, everything checks out in this equation. The results of what we have done so far can be summarized like this. Quasi-statics basically involves, okay, assuming static okay, assuming that everything is static, find out E0, okay, find out D0, find out H0 and find out B0. All the additional things like EMF or the magnetomotive force, electric flux density psi electric, magnetic flux density phi mag can also be found from these set of equations once I know. Of course, you also need to use the current continuity equation, okay, and this current continuity equation is dq by dt. Everything is varying with time, but the time variation is quite slow. Okay. Once you know this, then in the first order, so this is my 0th order. For the first order, what I do is I use E0 and D0, which I know already, to calculate H1 and B1. Okay. The reason why you will have H1 and B1 which is different from H0 and B0 is because the moment you allow D0 to be varying with time, there will be displacement current, and the displacement current varying with time will create magnetic fields, right. So, displacement current creates magnetic fields, and these magnetic fields now create H1 and B1 will create E2 and D2, because at this stage we still assume that E0 and D0 are the same. So, it will create E2 and D2, we will again assume H1 and B1 are the same. Okay. So, this way you can successively build up to the different orders of electric and magnetic fields, and in fact write down the total electric field as E0 plus E1 plus E2 and so on. Similarly, for the magnetic field H as H0 plus H1 plus H2 and so on. Feel free to stop at any order in which you do not really find much use. For example, you have found out up to E100, let us say you find out what will happen at E of 101, that is the order 101 field, but if the ratio of E101 to E100, okay, is quite small, if you express this in percentage, you might express this in this way, or you can actually express the difference between the two, right. So, E100, E101 normalize with respect to E100, if this relative value is less than say 1%, something that one is given already. So, let us say if it is 1%, 0.1%, depending on the problem that has been given to you, you can stop calculating the further orders. The whole point of what I wanted to try and express to you was that if you understand quasi-statics, you will be able to build up to the solutions in stepwise manner or in series manner. In fact, formally this is called as perturbation series, and these order terms that you are calculating are the perturbation terms. Okay. And you will have to stop the perturbation series, because otherwise it will continue all the way to infinity once you do not find any significant difference from say 100 to 101 or 200 to 201 and so on. There is a nice exercise that will evaluate the EMF for you if I have given you the values of V of t. Let me just mention the results of that exercise. Suppose I assume V of t to be some amplitude, whatever the amplitude, let us say 100 volt amplitude, and it is a cosine wave, okay, varying as cos omega t plus theta, and we will assume that omega, which is 2 pi f, has a frequency of 100 megahertz. So, this is quite clearly a very large frequency. Okay. The plate distances are say 1 mm, and the plate radius is given by 10 centimeter. This is clearly quite a large ratio, right. If you look at the radius, which is 10 centimeter, to the height, which is 1 millimeter, you will see that this would be something like 10 into 10 to the power minus 2. My math has gotten rusty, so please forgive me this. So, this would be 100 times, right. So, since this is 100 times, the area is 100 times or the radius is 100 times to the height, one can reasonably assume that fringing fields can be neglected and carry out the analysis that we have carried out. The goal here would be to try and find out what is the EMF, okay. What is the EMF, assuming that mu is equal to mu 0 and epsilon is equal to epsilon 0. So, you can assume everything to be air filled, or let us say assume mu is equal to mu 0, assume epsilon to be equal to 3 times epsilon 0. So, it simply means that you are assuming the dielectric constant to be 3. Okay. If you find the EMF, okay, and find the difference between EMF at 0 and EMF at A, both of these terms can be obtained from the expression for EMF that I have. EMF at 0 is this fellow, EMF at r equal to A can be obtained by substituting r equal to A, at which point the second term drops out, and that would be equal to V of t. So, the difference term is simply equal to mu 0 epsilon by 4 a square d square v by dt square. So, if you evaluate this difference, which will turn out to be mu 0 epsilon by 4 d square v by dt square term, right. So, that is the term that you are going to get times a square. Okay. So, substituting all these values and knowing that d square v by dt square actually goes as minus omega square times v of t itself, because cos omega t, once differentiation becomes sin omega t, omega sin omega t, next time differentiation becomes omega square with an appropriate minus term. So, the difference which would be this quantity actually turns out to be 3.29 volts. The volt that you have assumed would be the assumed or applied voltage is 100 volts, whereas the difference is turning out to be 3.29 volt across the capacitor. So, the EMF here is 100 volts, the EMF here is 100 minus 3, which is say 97 volts. Okay. So, this difference is 3, which is I am approximating, of course. So, this difference is 3. So, what you see is that there is essentially about 3% of change in the actual EMF values. Okay. So, if this 3% is large, then you are really not in the static regime, but for your application, if 3% happens to be small, then you are in the quasi static regime. There are additional things that one can do. You had a capacitor, then you can show that the capacitor actually also includes an inductor as its equivalent circuit because of this non uniform effect, but that is something that we will leave for an exercise. Okay. The point here was that you can construct the solutions of E or H using quasi static up to the desired order, up to desired accuracy, that would be a better word to say. Thank you.